Let's face it, computers are everywhere. You come into contact with them at home, work, the airport, the grocery store. You're using some kind of computer to take this course. You know what? There's probably one in your pocket right now. While computers are complex and can seem daunting to learn, they ultimately just calculate, process, and store data. In this lesson, we're going to take a peek at what's inside of a computer. We'll spend the next few lessons explaining how each of these components work. But for now, let's check out a typical desktop setup. Desktops are just computers that can fit on or under our desks. So here we have a monitor, a keyboard, a mouse, and a desktop. Sometimes we might even add a webcam, speakers, or a printer setup. We'll call these physical components hardware. Let's take a look at the back of a computer. You can see common connectors here. The power outlet here, and the common ports here. Ports are connection points that we can connect devices to that extend the functionality of our computer. We're going to detail about the ports you see here in a later lesson, but here's a quick rundown. We have a port here to connect to a monitor, and a few ports here to plug your keyboard and mouse. There's another important one here for our network connection. With just these ports, we're able to have the basic functionality to browse the web and much more. Things look pretty similar on a laptop. Here are some of the same ports. A built-in monitor, and a keyboard. There are also physical components inside the laptop case that are hidden for portability. Once you figure out how one computer works, you can figure out how any other computer works. Okay, this is my favorite part. Let's open up this desktop and take a deeper look. Let me first clean up my desk. Get ready for it. Whoa, it looks pretty complicated, but that's okay. We'll take you through it. Let's start with a quick tool. Then we'll dive deeper into each of these parts in the next lesson. Right here, this component is a CPU, or central processing unit, which is covered by this heatsink. You can think of the CPU as the brain of our computer. The CPU does all the calculations and data processing. It communicates pretty heavily with this component right here, RAM, or random access memory. RAM is our computer's short-term memory. We use this component when we want to store data temporarily. Let's say you're typing something to a chat, or a piece of text in a word processor. This information is stored in the RAM. Don't worry, we'll cram in more details on RAM in a later lesson. When we want to store anything in long-term memory, we use this component here, the hard drive. The hard drive holds all our data, which can include music, pictures, applications. Let me show you something else interesting. Have you noticed this lunch lab here? This is our motherboard. It holds everything in place and lets our components communicate with each other. It's the foundation of our computer. You can think of the motherboard as the body or circuitry system of the computer that connects all the pieces together. The last component we'll talk about is our power supply, which converts electricity from our wall outlet onto a format that our computer can use. You know what's interesting? All these components make up most computers, even a mobile phone. While it might look very different from your laptop, a mobile phone just uses a smaller version of the hardware that we saw in the desktop and laptop today. Understanding how computer hardware works is a really helpful skill set in IT support. Since an IT department maintains the hardware that a company uses, a solid understanding of these computer internals will come in handy when troubleshooting hardware-related problems. And taking things apart to see how they work is just super fun. Before we get our hands dirty learning how to build a computer, let's talk theory first. In an earlier lesson, we talked about binary and how computers perform calculations. Remember that our computer can only communicate in binary using ones and zeros. Our computers speak in machine language, but we, of course, speak in human languages like English, Spanish, Mandarin, Hindi. You get the idea. If we want to communicate with our machines, we have to have some sort of translation dictionary. Just like if I wanted to say something in Spanish, I'd look it up in an English to Spanish dictionary. Well, our computers have a built-in translation book. In this lesson, we'll dive deeper into how our computer translates information we give it into instructions that it understands. Right now, you're probably using a web browser, music player, text editor, or something else on your computer. We interact with these applications on a daily basis. They're referred to as programs. Programs are basically instructions that tell the computer what to do. We typically store programs on durable media like hard drives. You can think of programs like cooking recipes. We keep these recipes all stored together in a cookbook, just like apps stored in a hard drive. Now, we want to make a ton of food, so we hire a chef to follow our recipes and whip up something good. The faster our chef works, the more food she'll prepare. The chef is our CPU. She processes the recipes we send her and makes the food. Our chef works super fast, so fast that she can cook faster than she can read. So, we take a copy of the recipes and put them into RAM. Remember that RAM is our computer's short-term memory. It stores information in a location our CPU can access faster than it could with our hard drive. Now we can give our chef 1 or 2 recipes at a time instead of sending the entire cookbook to her. Okay, now let's say I want to make a peanut butter and jelly sandwich. I see a pretty good recipe and send it to our chef to make. Remember that our chef needs these instructions quickly, so I don't send her the entire recipe. I send her one line at a time. 1. Get 2 slices of bread. 2. Put peanut butter on one slice. 3. Put jelly on another slice. 4. Combine the 2 slices of bread. Now, let me throw one more thing at you. Our chef can only communicate with us in ones and zeros. So instead of sending something readable, like the recipe for a peanut butter and jelly sandwich, we have to send her something like this. In reality, this process is a little more complicated. Our CPU is constantly taking instructions and executing them. These instructions are written in binary. But how do they travel around the computer? In our computer, we have something called the external data bus, or EDB. It's something like a plus at all. It's a row of wires that interconnect the parts of our computer, kind of like the veins in our body. When you send a voltage to one of the wires, we say the state of the wire is on, or represented by a 1. If there's no voltage, then we say that the state is off, represented by 0. This is how we send around our ones and zeros. Sound familiar? In the last lesson, we talked about how transistors help us to send voltages. Now, we know how our bits physically travel around the computer. The EDB comes in different sizes: 8-bit, 16-bit, 32, even 64. Can you imagine if you had 64 wires going? You can move around a lot more data. Right now, we're just going to stick with using an EDB with 8 bits in our examples, sending 1 byte at a time. Okay, so now our CPU is receiving a byte and it needs to get to work. Inside the CPU, there are components known as registers. They let us store the data that our CPU works with. If, for example, our CPU wanted to add 2 numbers, one number would be stored in register A. Another number would be stored in register B. The result of those 2 numbers would be stored in register C. Imagine, the register is one of our chef's work tables. Since she has a place to work, she can start to cook. To do so, she uses a translation book to translate her binary to tasks that she can perform. Let's jump back for a second. Remember that our programs are copied into RAM for the CPU to read. RAM is memory that's randomly accessed, allowing our CPU to read from any part of RAM as quickly as any other part. We don't actually send data from RAM over the EDB. There would be way too much stuff. RAM can hold millions, even billions of rows of data. Despite our our sandwich example, most of our recipes aren't simple at all. They can be thousands of lines long. We want to process them and we don't actually go in any particular order. Since we can only send one line of data through the EDB at a time, we need the help of another component, the memory controller chip, or MCC. The MCC is a bridge between the CPU and the RAM. You can think of it like a nerve in your brain connecting to your memories. The CPU talks to the MCC and says, hey, I need the instructions for step number 3 of this recipe. The MCC finds instructions for step number 3 RAM, grabs the data, and sends it through the EDB. There's another bus that's nothing like a bus. It's called in the process called the address bus. It connects the CPU to the MCC and sends over the location of the data, but not the data itself. Then the MCC takes the address and looks for the data, and then data is then sent over the EDB. Believe it or not, RAM isn't the fastest way we can get more data to our CPU for processing. The CPU also uses something known as cache. Cache is smaller than RAM, but it lets us store data that we use often and lets us quickly reference it. Think of RAM like a refrigerator full of food. It's easy to get into, but it takes time to get something out. On the flip side of that, cache is like the stuff we have in our pockets. It's used to store recently or frequently accessed data. There are 3 different cache levels in a CPU, L1, L2, and L3. L1 is the smallest and fastest cache. So now we understand how our RAM interacts with our CPU. But how does our CPU know when a set of instructions ends and a new one begins? Our CPU has an internal clock that keeps its operations in sync. It connects to a special wire called a clock wire. When you send or receive data, it sends a voltage to that clock wire to let the CPU know it can start doing calculations. Think of our clock wires as the ticking of a clock. For every tick, the CPU does one cycle of operations. When you send a voltage to the clock wire, it's referred to as a clock cycle. If you have lots of data you need to process in a command, you'll need to run lots of clock cycles. Have you ever seen a CPU in the store and it has something labeled 3.4 DHZ? This number refers to the clock speed of the CPU, which is the maximum number of clock cycles that it can handle in a certain time period. 3.40 gigahertz is 3.4 billion cycles per second. That's super fast. But just because it can run at this speed doesn't mean it does. It just means that it can't exceed this number. Still, that number doesn't stop some people from trying. There's a way you can exceed the number of clock cycles on your CPU on almost any device. It's referred to as overclocking, and it increases the rate of your CPU clock cycles in order to perform more tasks. This is commonly used to increase the performance in low-end CPUs. Let's say you're a gamer and you want to have better graphics and less lag while playing. You might want to overclock your CPU when you play the game. But there are cons to doing this, like potentially overheating your CPU. CPU cache and overclocking. In this reading, you will learn about the various levels of cache for central processing units, CPUs, and how a CPU processes and executes instructions. Additionally, you will learn about overclocking CPUs to maximize processing speeds. IT support professionals may use this information when purchasing, allocating, and/or configuring high-performance servers. Cache. You may already be familiar with the term cache. In computer jargon, cache, pronounced cache, refers to a small amount of recently used data that is stored either on hardware or in software. The first time data is accessed, both the initial request for the data and the reply containing the data pass through multiple points on their journey. Depending on several variables, these points might include I/O devices, motherboard buses, RAM, cables, hard drives, applications, networks, the internet, cloud platforms, and more. If a computer needed to use these full paths every time it tried to access data, the entire transaction could take a relatively long time. Cache speeds up this process by holding a local copy of the most recently accessed data in temporary storage. CPU cache. CPUs use a system of cache storage to help them quickly access data. A CPU cache is normally stored inside each core of the CPU. Older computers might store CPU cache in a transistor chip that is attached to the motherboard, along with a high-speed bus connecting the chip to the CPU. CPU levels of cache. There are 3 levels of CPU cache memory. Level 3 cache. L3 cache is the largest and slowest of CPU cache. However, it is often twice as fast as RAM. L3 is the first CPU cache location to store data after it is transferred from RAM. L3 cache is often shared by all of the cores in a single CPU. Level 2 cache. L2 cache holds less data than L3 cache, but it has faster access speeds. L2 holds a copy of the most recently accessed data that is not currently in use by the CPU. Each CPU core normally has its own L2 cache. Level 1 cache. L1 cache is the fastest and smallest of the 3 CPU cache levels. L1 holds the data currently in use by the CPU. Each CPU core usually has its own L1 cache. Overclocking a CPU. Overclocking a CPU sets it to run at a higher CPU clock frequency rate than the manufacturer's original specifications. For example, if a processor is labeled as having a 3.2 GHz base frequency rate, it may be possible to overclock the CPU to run at 3.5 GHz. Achieving a higher CPU clock frequency rate means the CPU can process a higher volume of instructions per nanosecond, resulting in faster performance. A computer user might want to overclock their CPU to improve sluggish speeds when performing processor-intensive tasks like video editing or gaming. Overclocking a CPU's frequency involves 3 variables. The base CPU clock frequency, often measured in gigahertz. The core frequency, which is calculated by multiplying the base frequency by the CPU core multipliers. The core voltage, which needs to be increased in small increments to meet the increasing power demand of the CPU during the overclocking process. Warnings on overclocking. Overclocking the CPU can damage the computer if not configured properly. Operating a CPU at a higher speed can overheat the CPU and surrounding hardware, which can cause the computer system to fail. Additionally, overclocking the CPU can shorten the overall lifespan of the computer and void the computer's warranty. It is better to avoid overclocking the CPU and instead purchase the appropriate CPU speed necessary to meet computing demands. How to overclock a CPU safely. As an IT support professional, you may be asked to overclock a CPU. There are steps you should follow to do this as safely as possible. Always make sure that the requester understands the risks of overclocking before agreeing to perform this procedure. Check if overclocking is supported. First, make sure the CPU is a model that is unlocked for overclocking. Not all CPUs can support overclocking, including most laptop CPUs. Check the CPU manufacturer's documentation to determine if overclocking is possible for the CPU model. Both Intel and AMD provide overclocking guides and tools for supported CPU models. See below for links to these guides. Additionally, check the documentation for the computer's motherboard model to ensure that it can support an overclocked CPU. Clean the inside of the computer. Turn off and unplug the computer. While wearing an anti-static wristband, open the computer and use compressed air to remove any dust buildup that has accumulated. It is especially important to remove any dust from around the CPU, fans, and intake vents. Ensure an appropriate CPU cooler is installed. Critical. If the computer has a stock CPU cooler, it is most likely insufficient for cooling an overclocked CPU. Replace the stock CPU cooler with an advanced cooling system, like a liquid cooling system. Follow the manufacturer's instructions for overclocking the CPU. Using the detailed instructions from the manufacturer, see below for links to Intel and AMD's guides. Use benchmarking software to establish a baseline for the normal performance of the computer. Set each CPU core multiplier to the value of the lowest multiplier using either the manufacturer's overclocking software, recommended, or the BIOS. Then reboot the computer. Increase each CPU core multiplier by 1 to increase the CPU frequency. Test each increase for stability using the testing utility provided by the manufacturer. Fix any problems flagged by the testing tools, especially temperature alerts. If the system becomes too unstable, roll back to the last frequency that produced a stable performance and stop overclocking the CPU. If the voltage appears to become insufficient to support the new frequency, increase the voltage by 0.05 volts. Do not increase the voltage above 1.4 volts without specialized cooling hardware. If the
computer freezes or crashes, it has either become completely unstable or the CPU is not getting enough voltage to support the overclocked frequency. Use the BIOS to return to the last stable frequency, or increase the voltage in 0.01 volts increments until stable. If stable, reboot the computer before attempting the next increase. Resources for more information. Intel, overclocking. Maximize your performance. Intel's all-inclusive guide to overclocking CPU, RAM, and motherboard. The site also provides utility tools for fine-tuning overclock performance Intel CPU models that support overclocking. AMD Ryzen Master Utility for overclocking control. AMD's toolkit for overclocking Ryzen processors. Note that overclocking support for non-Ryzen models is no longer recommended by AMD. AMD Ryzen processor overclock memory compatibility list. List of AMD Ryzen CPU models that support overclocking. AMD, how to overclock your AMD Ryzen CPU. Instructions for overclocking AMD Ryzen CPUs from PC Magazine.
Changes in diversity with regards to IT support specialists is something I've noticed in the last several years. There's a lot of stereotypes in the industry. What I think was unexpected was how many people actually break them. The people I met, of course, my IT support career have clearly shown that it's not just all men. It's people from all walks of life. And that's one thing about IT support in general is that it's just so approachable for everyone. The diversity within the role has exploded. It's a much more diverse team now, both from the gender, the race background, as well as just educational background. I work closely with people from all different experiences all over the world, very different perspectives. It's great for the role, it's great for the company, but it's also great to just work with different people. It's an incredible experience to share my experiences with a teammate from Romania, a teammate from Kenya. It's refreshing, it's fun. I'm starting to finally lose those stereotypes associated with IT. I'm starting to kind of understand that technology is ubiquitous, everyone uses it. Why can't everyone support it as well?
If someone asked you, calculate the square root of 5,439,493, would you do the math by hand? Unless you really love tedious math problems, you'd probably use a calculator. What about binary? Well, you probably wouldn't calculate binary by hand either. There's actually a very powerful calculator right inside of your computer that processes binary for us. We've already discussed this in calculator in detail. Do you know what it is? It's our CPU, the brain of our computer. In this video, we'll cover the more practical aspects of the CPU. Remember that translation book that I talked about in an earlier lesson? The CPU uses this to translate and perform functions on our data. This translation book is called an instruction set, which is literally just a list of instructions that our CPU is able to run. Functions like adding, subtracting, copying data are all instructions that our CPU can carry out. Every single program on your computer, while extremely complex, is broken down into very small and simple instructions found in our instruction set. Instruction sets are hard-coded into our CPU, so different CPU manufacturers may use different instruction sets, but they generally perform the same functions. It's like how car manufacturers build their engines differently, but they all get the same job done. You probably work with computer hardware as an IT support specialist, replacing failed hard disks, upgrading RAM modules, and installing video cards. So you need to be aware of what's out there. You've probably heard of a few popular CPU manufacturers or chipsets, like Intel, AMD, and Qualcomm. These CPU manufacturers use different part names to differentiate their processors, like Intel Core i7, AMD Athlon, Snapdragon 810, Apple A8, and more. Now when you hear these terms, you'll know what they mean. Each of these CPU manufacturers have their strengths and weaknesses. If you're interested in learning more about why some CPUs are more popular than others, you can check out the next supplemental reading. When you select your CPU, you need to make sure it's compatible with your motherboard, the circuit board that connects all your components together. Heads up, you can't just buy a bunch of parts and expect them to work together. There are different ways CPUs fit on motherboards using different sockets. Your CPU might have lots of tiny pins that either stick out or have contact points that look like dots. Depending on your motherboard, you need to make sure these CPUs fit correctly in the socket. There are currently two major types of CPU sockets, land grid array, also known as LGA, and pin grid array, also known as PGA. In an LGA socket like this one, there are pins that stick out at the motherboard. The socket size may vary, so always make sure your CPU and socket are compatible beforehand. When you purchase a CPU or motherboard, they'll tell you right on the box what type of socket it has. Make sure your CPU and motherboard socket also both match. If it's not listed on the box, you can go to the manufacturer's website, where it usually lists what types of CPUs are compatible with the motherboard. The other type of socket is the PGA socket, where the pins are located on the processor itself. When we install our CPU, we need to do a few things to it to keep it cool. Since it does a lot of work, it's prone to overheating. We have to make sure to include a heatsink too, which takes the heat from our CPU and dissipates it through a fan or another medium. There's one last thing I want to call out about CPUs. If you purchase a CPU, you'll see that it has either a 32-bit or 64-bit architecture. What does that mean? Well, we know we can process 8 bits in binary. Now, imagine how we can process 32 or even 64 bits. CPUs that have 32-bit or 64-bit architecture are just specifying how much data they can efficiently handle. For now, the main takeaway is that the CPU is one of the most important parts of the computer, so we have to make sure it's compatible with all other well for our computing needs.
To learn more about the differences between 32-bit and 64-bit CPU architecture, click here.
Let's talk about RAM, our computer's short-term memory. We use RAM to store data that we want to access quickly. This data changes all the time, so it isn't permanent. Almost all RAM is volatile, which means that once we power up our machines, the data stored in RAM is clear. Remember that our computer is comprised of programs. To run a program, we need to make a copy of it in RAM so our CPU can process it. When you see a new phone or laptop that has 16 gigs of RAM, that means it can run up to 16 gigs of programs, meaning you can run lots of programs at the same time. When you type in a document, you're using RAM. If you've ever had the misfortune of working on an important presentation or paper and losing power, you know the feeling you get when all of the work you've done is lost. It's a total bummer. This happens to anything with RAM, even video games. Have you ever gone on a long campaign without saving? Then right as you get to a save point, the power goes off on console and all the progress you made is lost forever? It's no fun at all. You spend the next hour or so deciding whether or not just to rage quit the game completely and start all over from scratch. Not that this happened to me or anything, that was just a friend. Anyway, all of this happens because RAM clears its data when powered off. There are lots of types of RAM, and the one that's commonly found in computers is DRAM, or Dynamic Random Access Memory. When a 1 or 0 is sent to DRAM, it stores each bit in a microscopic capacitor. This is either charge or discharge, represented by 1 or 0. These semiconductors are put into chips that are on the RAM and store our data. There are also different types of memory sticks that DRAM chips can be put on. The more modern DIMM sticks, which usually stands for Dual Inline Memory Module, have different sizes of pins on them. I should call out, we don't really buy RAM based on the number of DRAM chips they have. They're labeled by the capacity of RAM on a stick, like an 8 gig stick of RAM. After DRAM was created, RAM manufacturers built something called SDRAM, which stands for Synchronous DRAM. This type of RAM is synchronized to our system's clock speed, allowing quicker processing of data. In today's system, we use another type of RAM called Double Data Rate, SDRAM, or DDR SDRAM for short. Most people refer to this RAM as DDR, even shorter. There are lots of iterations of DDR, from DDR1, DDR2, DDR3, and now DDR4. DDR is faster, takes up less power, and has a larger capacity than earlier SDRAM versions. The latest version, DDR4, is the fastest type of short-term memory currently available for your computer.
So choose between 64-bit, 32-bit version of Office. You can run add-ins or MDE files compiled in a 32-bit version of Office or Microsoft on a 64-bit version of Office or Microsoft and vice versa. I know which version I want. How do I install it? 64-bit version of 365 is automatically installed unless you explicitly select 32-bit version before beginning the installation process. To install either 32 or 64 of follow the steps in install Office on a PC. If you're still not sure which version, reasons to choose 64-bit. Computers running 64-bit Windows generally have more resources such as processing power, memory. 32-bit, also 64-bit application can access more memory than 32. 18.4 petabytes. Therefore, if your scenarios include large files and large data sets and your computer is running 64-bit version of Windows, then it's the right choice for you. If you're working with large data sets like enterprise scale Excel workbooks with complex calculations, many pivot tables, data connections to external databases, pivot, power pivot, 3D map, power view, get and transform, 64-bit version of Office is in these cases. Excel specification limits, data model specification limits, memory usage, and 32-bit edition of Excel. You're using add-ins with Outlook, Excel, or other Office Microsoft 365. While 32-bit application can work with add-ins, they can use up a system's available virtual address space, while with 64 bits you have up to 128 terabyte of virtual address space, which the app and any add-ins running the same process can share. With 32 bits apps, you might get as little as 2 GB of virtual address space, which in many cases is not enough and cause the app to stop or respond and crash. You're working with extremely large pictures, videos, animations, PowerPoint. 64-bit version of Office may be better. You're working with files over 2 GB, especially many sub-projects. You're developing in-house 365 like add-ins or Document level customization using 64-bit version of 365 lets you deliver a 64-bit version of those solutions as well as 32-bit version in-house. The 365 solution developers should have access to 64-bit Office 2016 for testing. You're working with large number data in access while data type is supported 32-bit access. You may see unexpected results when executing code or expressions that use native 32-bit VBA libraries. 64-bit VBA provides long data type which fully supports large numbers. Reasons to choose the 32-bit 64-bit Windows 10 with ARM-based processor, 32-bit operating system with x86 32-bit processor larger than 4 GB RAM. If you have 64-bit OS with x64 based processor, you can choose to install 32-bit on 64-bit Microsoft 365. IT professionals and developers in particular should also review the following situations when the 32-bit version of 365 is still the best choice for you or your organization. You have 32-bit COM add-ins with no 64-bit alternative. You can continue to run 32-bit COM and add-ins in 32-bit Microsoft 365 on 64-bit Windows. You can also try contacting COM add-in vendor and requesting 64-bit version. Use 32-bit controls with no 64-bit alternative. You can continue to run 32-bit controls in 32-bit 365. mscomctl.ocx, comctl.ocx, or any existing third-party 32-bit controls. Your VBA code uses declare statements. Most VBA code doesn't need to change when using 64-bit or 32-bit unless you use declare statements to call Windows API using 32-bit data types like long for pointers and handles. In most cases, adding PTR safe to the declare and replacing long with long PTR will make the declare statement compatible with both 32 and 64-bit. However, this might not be possible in rare cases where there is no 64-bit API to declare. For more information about what VBA changes are needed to make it run on 64-bit Microsoft 365, 64-bit Visual Basic for applications overview. You have 32-bit MAPI applications for Outlook, with a growing number of 64-bit Outlook customers rebuilding 32-bit MAPI applications. Add-ins or macros for 64-bit Outlook is the recommended option, but if needed, you can continue to run them with 32-bit Outlook only as well. To learn about preparing Outlook applications for both 32 and 64-bit platforms, see building MAPI applications on 32-bit and 64-bit platforms and the Outlook MAPI reference. You're activating a 32-bit OLE server or object. You can continue to run your 32-bit OLE server application with the 32-bit version of 365 installed. You need 32-bit Microsoft Access.md.ade.accde database files. While you can recompile 32-bit md.md.ade.accde files to make them 64-bit compatible. You can continue to run 32-bit .md.ade.accde files in 32-bit access. You require legacy equation editor, WLL, Word add-in libraries files in Word. You can continue to use legacy Word equation editor and run WLL files in 32-bit Word. You have an old embedded media file in your PowerPoint presentation with no available 64-bit codec. To install either 32 or 64-bit 365, follow In 2020, the first DDR5 RAM was made commercially available.
And faster RAM means that programs can be run faster and that more programs can run at the same time. Keep in mind that any RAM sticks you use need a compatible motherboard with a different number of pins aligned with the motherboard RAM slots. Just like with the CPU, make sure that your motherboard is compatible with any RAM sticks that you buy. Up next, we'll take a deep dive into motherboards. The motherboard, the foundation that holds our computer together. It lets us expand our computer's functionality by adding expansion cards. It routes power from the power supply, and it allows the different parts of the computer to communicate with each other. In short, it's a total boss. Every motherboard has a few key characteristics. First is the chipset, which decides how components talk to each other on our machine. The chipset on motherboards is made up of two chips. One is called the North Bridge that interconnects stuff like RAM and video cards. The other chip is the South Bridge, which maintains our I/O or input-output controllers, like hard drives and USB devices that input and output data. In some modern CPUs, the North Bridge has been directly integrated into the CPU, so there isn't a separate North Bridge chipset. The chipset is a key component of our motherboard that allows us to manage data between our CPU, RAM, and peripherals. Peripherals are the external devices we connect to our computer, like a mouse, keyboard, and monitor. In addition to the chipset, motherboards have another key characteristic, which allows the use of expansion slots. Expansion slots also give us the ability to increase the functionality of our computer. If you want to upgrade your graphics card, you can purchase one and just install it on your motherboard through the expansion slot. The standard for an expansion bus today is the PCI Express, or Peripheral Component Interconnect Express. A PCIe bus looks like a slot on the motherboard, and a PCIe base expansion card looks like a smaller circuit board. The last component of motherboards that we'll discuss is form factor. There are different sizes of motherboards that are available today. These sizes, or form factors, determine the amount of stuff we can put in it and the amount of space we'll have. The most common form factor for motherboards is ATX, which stands for Advanced Technology Extended. ATX actually comes in different sizes too. In desktops, you'll commonly see full-size ATXs. If you don't want to use an ATX form factor, you could use an ITX, or Information Technology Extended form factor. These are much smaller than ATX boards. For example, the Intel NUC uses a variation of the ITX board, which comes in three board sizes: Mini ITX, Nano ITX, and Pico ITX. When building your computer, you'll need to keep in mind what type of form factor you want. Do you want to build something small that can't handle as much workload? Or do you want a powerhouse workstation that you can add lots of functionality to? The form factor will also play a role into what expansion slots you might want to use. Understanding motherboards and their characteristics can be a big plus when fixing hardware issues, since things like the type of RAM module or processor are dependent on the kind of motherboard they need to fit into. Let's say you're responding to a ticket for a user who's having video problems. You don't want to make it all the way to the desk, only to realize the graphics card you bought as a replacement doesn't fit the motherboard their computer uses. So, before we get to computer storage, we need to fill in some gaps. We refer to things like gigabytes, bits, etc. But we actually haven't talked at all about what those metrics mean. Sorry, I think a bit ahead of myself. As you might have guessed, these terms refer to data sizes. The smallest unit of a data storage is a bit. A bit can store one binary digit, so it can store a 1 or 0. The next largest unit of storage is called a byte, which is comprised of 8 bits. A single byte can hold a letter, number, or symbol. The next largest unit is referred to as a kilobyte, but we typically use the term kilobyte. A kilobyte is made up of 1024 bytes. Here's a quick data conversion chart. How much does 500 gigabytes need to be? Let's take a look at the size of an average music file, which is about 3 megabytes. On a 500 gigabyte machine, that's approximately 165,000 music files. That's a lot of music. We store all of our computer data on our hard drive, which allows us to store our programs, music, pictures, etc. Have you ever had an issue with your computer and lost all the data that was on your hard drive? Yeah, me too. It was the worst. This actually happens a lot, and you'll probably encounter it as an IT support specialist. Make sure you back up your data to be safe. This means you should copy or save your data somewhere else, just in case something goes wrong in hard drive patches. That way, you won't lose all your data. There are two basic hard drive types used today. Hard disk drives, or HDDs, use a spinning platter and a mechanical arm to read and write information. The speed that the platter rotates allows you to read and write data faster. This is commonly referred to as RPM, or revolution per minute. A hard drive, the higher RPM is faster, so if you go out and buy a hard drive today, you might see something like a 500 gigabyte with 5400 RPM. HDDs are prone to a lot more damage because there are a lot of moving parts. This susceptibility to damage went away with a new type of storage called solid-state drive, or SSD. SSDs have no moving parts. Are you familiar with USB stick? SSDs operate in a similar way. The information is stored on microchips, and data travels a lot faster than HDDs. The form factor of SSDs is also slimmer compared to their HDD cousins. Sounds great, doesn't it? So why doesn't everyone use SSDs? Well, both have their pros and cons. HDDs are more affordable, but they're more prone to damage. SSDs are less risky when it comes to losing data, but they're also more expensive. So you may not buy as much memory storage SSDs than what you can get HDDs. Believe it or not, there are even hybrid SSD and HDD drives out there. They offer SSD performance being needed for things like system performance, such as booting your computer, along with hard disk drive, but less important stuff like basic file storage. There are a few interfaces that hard drives use to connect our system. ATA interfaces are the most common ones. The most popular ATA drive is a serial ATA, or SATA, which is one cable for data transfers. SATA drives are swappable. Great tech, don't you think? It means you don't have to turn off your machine to plug in a SATA drive. SATA drives move data faster and use a more efficient cable like this one than its predecessors. SATA has been the de facto interface for HDDs today, but people quickly found that using the SATA cable wasn't good enough for some of the blazing fast SSDs that were coming on the market. The interface couldn't keep up with the speeds of the US SSDs, so another interface that was created called NVMe Express, or NVMe. Instead of using a cable to connect your drive to your machine, the drive was added as an expansion slot, which allows for greater throughput of data and increased efficiency.
Data storage measurements. In this reading, you will learn about the different names for measurements of data storage capacities and file sizes. Data storage capacity increases in step with the evolution of computer hardware technology. Larger storage capacities allow for dynamic growth in file sizes. These advances make it possible for companies like Netflix and Hulu to store thousands of feature-length films in high video quality formats. There are standardized sets of terms used to name the ever-expanding sizes of data storage and files. For example, the common terms used to describe file sizes and hard drive storage capacity include bytes, kilobytes, megabytes, gigabytes, and terabytes. However, if you are a computer engineer, you might use a different set of terms. Data storage measurement nomenclature, decimal nomenclature, kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte. The decimal naming system for computer storage uses the metric system of prefixes from the International System of Units: kilo, mega, giga, tera, peta, exa, zetta, and yotta. These prefixes may also be referred to as the decimal system of prefixes. The metric decimal nomenclature represent a base 10 approximation of the actual amount of data storage bytes. The metric system prefixes were selected to simplify the marketing of computer products. Binary nomenclature: kilobyte, megabyte, gigabyte, terabyte, exabyte, zettabyte, yottabyte. The binary naming system is a standard set by the International Organization for Standardization (ISO) in partnership with the International Electrotechnical Commission (IEC). The ISO 8000 and IEC 8000 guides to units of measurement define the International System of Quantities (ISQ). The prefixes kibi, mibi, yibi-tibi, pibi, xb, zb, and yobi were created by the IEC organization. They are a blend of the first two letters of the metric prefix fused with the first two letters of the word binary. Example: megabyte plus binary plus byte equals mebyte. Binary measurements in computer data are more accurate than decimal system measurements. While decimal nomenclature is commonly used to market computers and computer parts to the general public, binary nomenclature is often used in computer engineering for numerical accuracy. Quantities of storage measurements. As data storage grows, the need for new terminology to describe the exponentially larger byte quantities grows too. The current byte nomenclature, mathematical representations, and storage capacities are as follows. 1 bit, also called a binary digit, bits store an electric signal as 1. The absence of an electric signal is stored as 0, which is also the default value of a bit. 1 bit can store only one value, either 1 or 0. These two possible values are the basis of the binary number system, base 2, that computers use. All numbers in a base 2 system increase exponentially as powers of 2. 1 byte. 1 byte stores 8 bits of 1s and 0s that translate to a symbol or basic computer instruction. Examples: 0110101 is the byte that translates to the letter M. The byte 0111111 tells the computer to delete the character to the right of the cursor. 1 kilobyte, 1 kilobytes. Kilobyte KB, decimal format, 103 equals 1000 bytes. Kilobyte B, binary format, 2 and 10 equals 1024 bytes. Decimal inaccuracy, off by -2.4% or -24 bytes. Name origin: kilo is a French derivation from the ancient Greek word for 1000. A kilobyte is 1000 bytes. 1 KBs can hold a short text file or a small icon as a 16 by 16 pixel.dif file. 1 megabyte, 1 megabyte. Megabyte MB, decimal format, 106 equals 1000 bytes. Megabyte MIB, binary format, 220 equals 1048,576 bytes. Decimal inaccuracy, off by 4.9% or -48,576 bytes. Name origin: mega is derived from the ancient Greek word for large. A megabyte is a large number of bytes. 1 megabyte can hold approximately 1 minute of music in a lossless data format or a short novel. 1 gigabyte, 1 gigabyte, GB decimal format, 109 equals 1000,000 bytes. KB binary format, 273,731,741, that's 824 bytes. Decimal inaccuracy, off by -7 and 4%, 23,724 bytes. Name origin: giga is derived from the ancient Greek word for giant. A gigabyte is a giant number of bytes. 1 gigabit can hold between 2.5 to 3 hours of music in MP3 format or 300 high-resolution images. 1 terabyte, 1 terabyte, terabyte, decimal format, 1012 equals 1,000,000 bytes. Tibibyte, TIB binary format, 240 equals 1,999,511,627,776 bytes. Decimal inaccuracy, off by 10%. Name origin: tera is a shortened form of tetra, which was derived from the ancient Greek word for the number 4. The 1 times 12 decimal format can also be written as 1004, 1000 to the 4th power. Tera, in ancient Greek, means monster. You might think of the word terabyte as a monstrously large number of bytes. 1 tera can hold approximately 200,000 songs in .mp3 format or 300 hours of video. 1 petabyte PB decimal format, 1015 equals 1,000,000 bytes. IB binary format, 250 to 1,125, 899,906, 840,624 bytes. Decimal inaccuracy, off by 12.6. Name origin: peta is derived from the ancient Greek word penta, meaning 5. The 115 decimal format can also be written as 1005, 1000 to the 5th power. 1 PB can hold the content from 1.5 million CD-ROM disks or 500 billion pages of text. 1 exabyte EB decimal format, 1018 equals 1,000,000 bytes. Exabyte EIB binary format, 260 equals 121,506 bytes. Decimal inaccuracy, off by 15.3%. Name origin: exa was derived from the ancient Greek word for 6. The 11018 decimal format can also be written as 1006, 1000 to the 6th power. 1 EB can hold approximately 11 million movies in 4K video resolution or 3,000 copies of the entire United States Library of Congress. 1 zettabyte ZB decimal format, 1021 equals 1,000,000 bytes. ZB byte, ZIB binary format, 270 equals 1,159, 1,006, and 20,707, 411, 324 bytes. Decimal inaccuracy, off by 18.1%. Name origin: zetta was derived from the Latin word septa, which means 7. The 1021 decimal format can also be written as 1007, 1000 to the 7th power. 1 ZB can hold. Seagate reports 1 zettabyte can hold 30 billion movies in 4K video resolution. 1 yottabyte YB decimal format, 1024 equals 1,000 bytes. Yobi byte YIB binary format, 280, 1,289, and 25,629, 174, 706, 176 bytes. Decimal inaccuracy, off by -20.9%. Name origin: yada is ancient Greek for 8. The 1024 decimal format can also be written as 1008. 1 YB can hold. In 2011, the cloud storage company estimated that 1 yottabyte could hold the data of 1 million data centers.
In order to get our computer to work, let's give it some power. Computers have a power supply that converts electricity from your wall to something useful. There are two types of electricity: DC, or direct current, which flows in one direction, and AC, or alternating current, which changes directions constantly. Our computers use DC voltage, so we have to have a way to convert the AC voltage from our power company to something we can use. That's what our power supply does. It converts the AC we get from the wall into low voltage DC power that we can use and transmit throughout our computer. So let's talk about power supplies. I actually have one right here. Let me show you what it looks like. That right here. So most power supply units have a fan, which is right in here. They also have voltage information, which is normally listed underneath or on the side, and cables, like this one, to power your motherboard, and a power cable. Have you ever plugged one of your devices into the wall outlet for your device? If you haven't, you're really lucky. After completing this lesson, hopefully you'll know how to avoid that situation. To understand electricity, let's use the example of water pipes. Our sinks have a faucet that's connected to a pressurized water tank. When we turn on the faucet, water comes out. This is sort of like how electricity works. When we plug an appliance into a water outlet and turn it on, a flow of electricity comes out. If we added more pressure to our water tank, would more water come out of it? The higher the pressure, the more water there will be. When it comes to electricity, we refer to the pressure as voltage. So when I was on vacation, to my surprise, when I plugged in a 120 volt appliance to a 220 volt outlet, the power came bursting through and fried my charger. If it was the other way around and a 220 volt appliance was plugged into a 120 volt outlet, I wouldn't have seen the same outcome. I'll still be able to get electricity, but slowly. This would be similar to if a water tank was only half pressurized, it would draw water, but slowly. In some cases, though, this can deteriorate the performance of the device and cause damage in the long term. As a general rule, be sure to use proper voltage for your electronics. We refer to the amount of electricity coming out as current or amperage, and it's measured in amps. We can think of amps as pulling electricity as opposed to voltage, which pushes electricity. Amps will pull as much electricity needed, but voltage will just give you everything. Look on the back of one of your device chargers. You might see something like doesn't mean that if you have a large power supply, you'll overpower your computer. Power supplies just give you the amount that your system needs. It's best to err on the side of large power supplies. You can power most basic desktops with a 500-watt power supply, but if you're doing something more demanding on your computer, like playing a high-resolution video game or doing a lot of video production and rendering, you'll likely need a bigger power supply for your computer. On the other hand, if all you're doing is just browsing the web, the power supply that comes with your computer should be fine. All kinds of issues are caused by a bad power supply. Sometimes the computer doesn't even turn on at all. Since power supplies can fail for lots of reasons like burnouts, power circuits, or even lightning strikes, knowing how to diagnose power issues and replace a failed power supply is a skill every IT support specialist should have in their toolbox.